This is section 5.3. Today we're going to talk about how to diagonalize a matrix, what that means, and when it is possible. We're going to skip doing powers of a matrix. All right, let's start with the review. Find the eigenvalues of this matrix. So remember, to find eigenvalues, you solve determinant A minus lambda I equals 0. That's called the characteristic equation. So in this case, we're solving the equation 0 is the determinant of A minus lambda I. So I take A and I subtract lambda off the main diagonal. And those straight bars mean determinant. All right, that's lambda squared minus 8 lambda plus 15, and then minus -1, so plus 1, is lambda squared minus 8 lambda plus 16, which is lambda minus 4 quantity squared. So our eigenvalue is lambda equals 4, and there's only one of them. And note that the algebraic multiplicity of lambda equals 4 is 2, because the exponent in the characteristic polynomial is a 2. Now let's find a basis for the corresponding eigenspace. So in this case, we want to solve A minus 4i times x equals 0. Now that's a matrix equation, so our answers will be vectors. And so we want to reduce A minus 4i augmented with 0. You want to show that in your work, like show what you're doing. I'll want you to do that on our next test. So A minus 4i. We subtract 4 off the main diagonal of A. We get -1, -1, 0, and then 1, 1, 0. And that reduces to 1, 1, 0, 0, 0, 0. So x2 is t, it's free, and x1 is -t. So a basis for the eigenspace is, we want the solutions look like, let me back up, solutions look like x bar equal t times -1, 1. That's the set of all solutions. So a basis for that would be the vector -1, 1. And since this basis has one vector in it, the dimension of the eigenspace is 1. So the geometric multiplicity is 1. All right, so this will be important to us later today because we're going to see, we're going to be comparing algebraic multiplicities to geometric multiplicities. But note here that the algebraic multiplicity is 2, geometric is 1. All right, now let's talk about diagonalization. Here's the definition. A square matrix is diagonalizable if it's similar to a diagonal matrix. And I don't know if you remember the definition of similarity, but here's a reminder. It means A can be written as P inverse D, AP, let me try one more time. A is PDP inverse, D is diagonal, P is invertible. And so the quick check, rather than finding P inverse to determine if you have P and D and you want to see if A is diagonalizable, the quick check would be multiply both sides by P and check is AP PD. That would be quicker than checking if A is PD P inverse. But what we'll be doing today is finding P and finding D. So we'll want D and we'll want P. We'll see how to do that. All right, so for example, this matrix here, A, is diagonalizable. I'm just claiming that, and I'm giving us D and P. And so rather than computing P inverse and checking if A is PD P inverse, you could check is AP PD. And I already checked, and the only reason I checked it just to show you that the AP is a fairly straightforward computation. You can do that, make sure you can actually do that. PD, we're multiplying by a diagonal matrix, and note that that scales the columns of P. So right multiplication by diagonal matrix scale the columns of P by the entries of D. And if we left multiply, we'll see at the end, if we left multiply by a diagonal matrix, that will scale the rows of a matrix. Okay, theorem 5. If we have a square n by n matrix, it's diagonalizable if and only if it has n linearly independent eigenvectors. So the example at the top of the page, this matrix A here is not diagonalizable. Here's why. It's a 2 by 2 matrix. It had a single eigenvalue 4, and for that one eigenvalue, there was only one linearly independent eigenvector because the basis had one vector in it. So we would have needed 2 linearly independent eigenvectors in order for A to be diagonalizable. So we don't have to diagonalize A in this case because it's not diagonalizable. If you have a diagonalizable matrix, here's how you're going to find P and D. And I've got the proof of this theorem at the end. Go ahead, find the eigenvalues. There might be repeat eigenvalues, but let's say lambda 1 through lambda n. And then find a basis for the eigenspace of each corresponding eigenvalue. And if you have n linearly independent eigenvectors, you're going to put those in a matrix, call it P, and the entries have to correspond to the entries of D. So if you put the values lambda 1 through lambda n in on D, you need to match up the eigenvectors to the eigenvalues in terms of how you order them. And I'll show you what I mean in this example. So we're going to diagonalize this matrix if it's possible, and we'll see that it is possible. So step 1, find the eigenvalues. I went ahead and put in 0 is determinant A minus lambda I. This matrix is not triangular, so we're actually going to have to find the determinant with cofactor expansion. I'll do cofactor expansion on row 1. So the determinant is 2 minus lambda times the subdeterminant 2 minus lambda 1, 0, 1 minus lambda. Okay, now the determinant of this matrix, this guy is triangular, so we can just multiply the diagonal entries. And so altogether we'll get 2 minus lambda squared times 1 minus lambda. All right, so our eigenvalues are 2 and 1. So we get lambda equals 2 and 1. And 2 is actually a repeat eigenvalue, so you could list 2 twice if you wanted to, but I would just say lambda equals 2 is an eigenvalue, and its algebraic multiplicity is 2. Now for each eigenvalue, we have to find a basis for the eigenspace. So for lambda equals 2, we need to solve A minus 2i times x equals 0. So I went ahead and wrote down, we want the augmented matrix A minus 2i augmented with 0. And that's going to be, coming up here, putting 2 in for lambda, we're going to get, although this is determinant, so these are straight bars, and here I want literally the matrix, so I'm using a matrix notation. We'll get 0, 0, 0 across the top, and then 1, 0, 1, and then negative 1, 0, negative 1, 0, 0, 0. Okay, and I'm going to do a couple steps at once. I'm going to kill off the third row, and I'm going to move the second row to the top. 1, 0, 1. And if I'm going too quick, pause it, make sure you can follow what I did. All right, so x3 is free. We'll call that t. x2 is also free. Let's call that s. And x1 will be negative t. So a basis for the eigenspace, we're going to want the one vector for the t's and then the one for the s's. So the t vector would be negative 1, 0, 1. And then the vector corresponding to the s variable is 0, 1, 0. And that's because the solutions look like t times negative 1, 0, 1 plus s times 0, 1, 0. Now I'm going to name these. I'm going to call this P1 and I'm going to call this P2. I'm going to name those two vectors. They'll be entries in the matrix P because those are eigenvectors. All right, for lambda equals 1, we want to solve a minus I times x equals 0. So the augmented matrix A minus I augmented with 0 is 1, 0, 0, 1, 1, 1, negative 1, 0, 0, and then 0, 0, 0. And if we reduce that, we can kill off these entries and we'll get 1, 0, 0, 0, 1, 1, 0, 0, 0. So x3 is free, x2 is negative x3, so negative t, and the top row reads x1 is 0. So basis for the eigenspace is 0, negative 1, 1. And I'm going to call that P3. All right, all the work is done. The grunt work is done. Now we're going to build a D and P. So for D, let's go up to the instructions. Find the eigenvalues and use these to form the entries of D. So our eigenvalues are 2, 2, and 1. And I'm saying 2, 2, and 1 because the algebraic multiplicity of lambda equals 2 is 2. So I'm going to list, in D, I'm going to list 2 twice on the diagonal. I'm going to go 2, 2, because it appears twice, and then 1. And then everything else is 0. If this were a 4 by 4 and the algebraic multiplicity of 2 were 3, then I'd have 3 2's down the diagonal. Now for P, we put in the corresponding eigenvectors. So the eigenvectors corresponding to 2 are P1 and P2. So I can put those in any order. I can go negative, I'm going to put in P1, negative 1, 0, 1, and then P2, 0, 1, 0. So P1 and P2. And then since I have the third eigenvalue in the last entry of D, I need to put P3 in as my last column. Okay, now those aren't the only options. Like suppose since I'm putting 2 and 2 in as the first two entries, I could have switched these and put P2 first and P1 second. Or if I want to put 1, the eigenvalue 1 in the middle and sandwich it by 2 2's, that would be fine. It's just I would have to put P3 in as the middle vector. And if I wanted the eigenvalue 1 in as my first entry of D, that's fine. I would just have to put in the corresponding eigenvector, which is P3, in as the first entry of P. I hope that makes sense. Okay, so pause the video and try diagonalizing this matrix. And to save time, and your homework does this on some problems too, I've already given you the eigenvalues. So you just need to find bases for the corresponding eigenspaces.